Okay, everybody. Today I'm gonna show you a tutorial about this paper LoRA. Perhaps you have ever heard of this paper. I think by 2021. Yes, it has been 2 years by now. So this is just a tutorial. I will not dive into this paper too deep. If you are interested in this paper, you can download this paper and explore more details. So this is just a tutorial. I will explain the method, the algorithm proposed by the author, and find some application of the algorithm LoRA and show you what the algorithm do and say something interesting. I'm gonna post some question, so hopefully we can find the answer from this paper, so we can answer my question. By doing this, we can understand this paper. So as you can see, the paper called LoRA. So what is LoRA? It's low rank adaptation of large language models. So through the title, we can see the paper is trying to solve problem about large language model. So briefly, the paper is trying to solve the training cost problem of large language model. You know, when we work into GPT period, the model is becoming large and large. So from the abstract, we can see GPT-3 has 175 billion parameter. It's very big. So if you want to retrain the model, the cost is very high. So this paper is basically trying to find a method that we can fine-tune the model through a Wemo chip way. So let's look at the abstract. The author said, compared to GPT-3 fine-tuned with Adam, LoRA can reduce the number of trainable parameters by 100 times and the GPU memory requirement by 3 times. So the algorithm reduces the trainable parameters. When we use less trainable parameter, that means we can save more cost of GPU memory and the computing. If you are interested in this paper, you can go to the GitHub and see the source code. So what is LoRA? As you can see in the website, there are some style photos. It's weird. So the photo is weird. So basically, if you want to get a specific style photo like this one, you need to train your own LoRA model. In the past, if you don't want to train LoRA, you need to fine-tune all the model. The cost is very high. When we use LoRA, we can leverage a Wemo chip way to fine-tune the model. So not only for the image generation, we can use the method to other large language model like GPT or Stable Diffusion or any other models. Okay, let's go ahead. Let's look at what the paper explained. So I wanna ask one question. Okay, from the abstract, we can say the LoRA is trying to solve a training problem related large language model. Not only large language model, any other deep learning model, we can use LoRA method. We can use the algorithm. So let's say how to LoRA solve the problem. Before we dive into the algorithm, let's look at the problem, the training problem. Yes, the problem statement. So we can see some detail about the training problem. Basically, this is the object function. Don't be scared. I know when we see the math formula, we will be scared. Okay, let's look at the every part of the formula. What is the So the title is problem statement. So this is the problem we want to solve. Okay. From the beginning we can see there's a max. So we want to maximize all the value computed by the formula. Where's our data? So as you can see, the x and y is our data. The x is the x is data and the y is label. And where's our predicted label? The yt is predicted label. We want to the predicted label as much as close to the target. So what I mean is we want to yt and y as close as possible. For every pair training data, we want to achieve this object. Yes, how many samples we have? So from here we can see we have a y amount of data. Okay, I will explain more about the detail. This formula is that how close our target and our predicted label, yes, how close they are. We want to the yt and y as close as possible. So this is the real value, real number that the close. Maybe the value is 0.1, 0.2, so something like that. And we gonna use a log function to this value. Why we use log function? Because this value is decimal. So I will make example. 0.1 multiply 0.1 equals 0.01. As you can see, two decimals multiplied, we generated a more smaller value. So but we can use log function, let this value get bigger, so our computer can handle this value. It is just a trick, so maybe you can ignore the detail. Yes, this is not very important. So basically this function is we want to achieve the object we want to achieve. We want the predicted label. We want the label as much close as the target table. Yes, this is the general machine learning problem, but it is just a math formula. Seems like it is complex, but actually it is not. Okay, let's look at the next part, the LoRA object function. So as you can see, the first function and the second question, as you can see, the first formula and the second formula is pretty similar. Yes, so I will erase this. Okay. The difference between the two formula is that it's this part. This is LoRA part. What LoRA do? It separates this parameter into this. Okay, I will make it more accurate. This file into two part. Okay. Original is file, and with LoRA we separate the file into two part. File 0 and start file. Okay. Okay, let's erase this. Let's clean up. The first part is our pre-trained model. Yes, pre-trained large language model. Basically, it is not updated. The parameter is not updated. We only updated the second part. It's very similar to, the last dense layer. For a traditional deep learning or machine learning problem, like BERT, like other machine learning problem, we can pre-train a model and we added another layer, like dense layer, softmax layer. We can keep the pre-trained parameter fixed. They are not updated like this one. And we added another dense layer. We fine-tuned the last layer like this. We updated it. We are going to update the parameter of the last layer. So it is very similar method. So this paper, from now, it seems like there's nothing new. Okay, let's look at the next part of the paper. What LoRA actually do? Okay, this is our method, basically LoRA method. This is the method. Okay, let's look at the description. So like we mentioned before, this is our model. We have a fixed parameter and another flexible parameter. We can update this part parameter and keep this one fixed. But the author said the LoRA decomposition the W matrix into B and A. Why do the author do that? Because B and A have a way lower rank. Yes, as you can see, the B has a dimension D plus R, and the A matrix belongs the dimension of A matrix is R multiply K, which means they have a rank R, and R is way less than the D and K. So why do the author do that? Because compared computing in the inference time or the training in the inference period or the training period, computing the dart W is very cost. But when we separate the matrix into B and A, okay, let's clean up. When we separate this matrix into this one, we can lower the cost. We can save the cost way much better. So why it is better? Because B and A have a lower rank. So why lower rank have a better computing efficiency? That's another topic. We can make another video to introduce this mathematical, the problem. Okay, so basically LoRA is simple. It is just the decomposition matrix. Okay, that is simple. Oh, okay, I will explain more about the detail. The X is our data, you know. X is our data. If we step back, H is hidden layer. It equals our W multiply X. W is our model, you know, it has some parameter. X is our data. So we pass the model with the data, we can get the predicted label. H is our predicted label. So we can use another statement that we can say what is W? W is W0 plus dot W X, and it is equal just this part. Okay. So what is dot W? W is dot W is just equals B multiply A. Yes. And in this part BA multiply X, the compute efficiency is very high. It saves more cost than we just use this one. Yes, this is better than we just multiply X with W. Okay, this is the paper. Okay, let's look at the okay, there's a lot of experiment, empirical experiment. Let's jump into the last diagram. Okay. The author compared different methods. So let's look at the first diagram. The first one is fine-tune. Yes. Okay, let's first look at the x-axis and the y-axis. X-axis is trainable parameter. That means we go right, the model go bigger. And the y-axis is validation accuracy. So we can say when we go up, the accuracy is more better. So as you can see, the fine-tune method is here. Yes, the fine-tune method needs update all the parameters. So the trainable parameter is on the right, and the accuracy is better than other method. So it makes sense. But it just cost a lot of the money. So let's look at the other method. From the diagram we can say this method is better because it just have a better accuracy. Yes, what this method? Okay, it is LoRA. LoRA is the best method. As you can see, the accuracy is very stable when the trainable parameter goes bigger and bigger. But the other algorithm, it just have a drop. The accuracy have a drop. Okay, as you can see, the second diagram, it is a little bit weird because the fine-tuned dot is the accuracy of fine-tuned method is worse than LoRA or this algorithm is a little bit weird. I think the fine-tuned method is the best one. Okay. The LoRA is also the best method of the Oh, for algorithm. Okay, let's look at this paper. Is there any other interesting place? So maybe this is the paper. It is not very difficult because and the method is very simple. It's just decouple the matrix, and the matrix, the cost of computing the matrix multiplying is lower than the original method. Okay. If you are interested in this paper, you can download this paper, but I don't want to dive into this paper too deep. It's just a tutorial. I will update some videos about some paper that I am interested. Maybe this is today's video. I will make some other large language model videos. If you like this video, please give me a like and leave a comments below. If you have some question, we can discuss the question. So maybe this is today's video. See you. Bye.